OK. Let's run the application. All right, let's start. Hello, everyone. Hope you're doing well. Welcome to this workshop series on artificial intelligence. So this workshop comprises 3 main courses related to the data science field. So the first one is an introduction to machine learning. The second one is an introduction to deep learning. And finally, an introduction to data visualization and Docker. Of course, today we're going to start with the first one, which is the machine learning course. But before we dive into the course, allow me first to introduce myself. So my name is Abdelghafour HALIMI. I have a PhD in image processing and artificial intelligence from the National Political Institute of Toulouse in France. And I was working as a data scientist for worldwide companies, such as Pierre Fabre and Atos in France. And I have over a decade of experience in the AI field, working for several projects on different fields, like remote sensing, medical imaging, computer vision, with major organizations, such as Airbus, CNES, or the European Space Agency, ESA. And I recently joined the Chaos Visualization Core Lab. So our Core Lab provides a lot of facilities and expertise in many fields. For example, my colleagues James and Thomas are specialized in 3D data visualization. My colleague Ronald is specialized in virtual reality. And me and Didier are specialized in the data science field. And finally, our manager Sohaib, who is specialized on creating advanced dashboards using advanced visualization tools. So don't hesitate to contact us. I put you a link here for our wiki page, where you can find more information and details about the different services that you are providing. You can check also our YouTube channel, where you can find the previous tutorials and training provided by me and my colleagues. All right, let's start from the top. What is machine learning? Machine learning is a very broad field. It contains many different aspects, and you're going to see a lot of definition of it online. But for the sake of this course, we're going to try to keep it as much as possible practical. So in a single sentence, machine learning is using an algorithm or computer program in order to learn some patterns in the data, and then using that algorithm and what it's learned in order to make some prediction on the future for new similar data. Now, machine learning algorithms are also called models. I'm going to use this term a lot later in the Jupyter Notebook examples. But you can ask then how machine learning algorithms differ from a normal algorithm. The answer is the learning aspects. Let's see an example. Where a normal algorithm could be a set of instructions of how to turn a pile of raw ingredients into your favorite chicken dish. For example, you're going to start by cutting the vegetables, season the chicken, preheat the oven, etc. And if you follow these steps correctly, you will end up by having your chicken dish. Now, what's important to note here is that a normal algorithm is going to start with an input, which is the ingredient here, and a set of instructions in order to get the output. Machine learning is different. Machine learning is going to start with an input and an ideal output, and they're going to try to figure out the right instructions. Now think about it. Maybe not going to work. For your first try, you're going to put a lot of spices, cook the chicken for 200 minutes. Second try, same thing. Some extra spices, cook the chicken for 100 minutes. Third try, still not working, but you start getting closer. Now, when it comes to machine learning, this process can take hundreds of tries and iteration. We call this epochs. And at some point, the algorithm is going to converge. You're going to find the right instructions. Now, I know that I'm missing skipping a lot of mathematical details behind this, but this is just a simple way to give you an idea how machine learning works in a nutshell. So keep in mind, machine learning is going to start with an input, ideal output, try to create some relationship between these two to learn some patterns in order to find the right instructions. And maybe next time that you're going to have some ingredient in your fridge and you don't know what to do with it, this algorithm can help you by giving you some idea about the dishes that you can make. All right, now what's the difference between data analysis and data science? Data analysis is trying to gain some understanding of the data by comparing different examples, different features, different visualizations, like graph, chart, histograms. On the other hand, data science is taking this a step further by doing a lot of experimentation on the data in order to gain some insight within it. One of the experiments that you can do is building a machine learning model. So as you can see, data analysis and machine learning are part of the data science field. Now, what you're gonna cover today? Again, as I said, I'm not gonna enter into the mathematical details behind this. We're gonna try to keep it as much as possible practical. This is what we are meant to do. So here we're gonna try to go and to see the most important steps in real machine learning projects. We're gonna go through these steps. And we're gonna, at the end, try to build a framework or pipeline in order that you can use it and adapt it for your own problem layer. Here, I try to summarize the most important steps in machine learning projects, real one. In general, machine learning comes in three main parts. First one is data collection, data modeling, and deployment. Data collection is how you're gonna get the data. Maybe by downloading it from servers, clouds, doing web scraping. Deployment is how you're gonna share your application or your model. Maybe by creating dashboards or creating API. And finally, the most important part, which is data modeling, and which we'll be focusing on this course. And we're gonna try to go through these different steps: problem definition, data, evaluation, features, modeling, and experiments. Let's start with the first one, problem definition. What problem are we trying to resolve? Now here, before I get into this and see the different main type of machine learning problems, I want you to know first that machine learning is not a solution to every problem. And it's not always the best choice. And I need you to know first when you shouldn't use machine learning. If a simple hand-coded instruction-based system work, go for it. Forget about machine learning. It's a waste of time. Don't do it. I mean, if we have already the instructions to get our chicken dish, this is the best model that you can have. Machine learning is gonna be a waste of time. On any other kind of scenarios, of course, machine learning could help, be useful and very helpful. Now, when you're gonna start a project, you're gonna have a business problem. And you're gonna need to match it to a machine learning problem. These are the main type of machine learning problems: supervised learning, unsupervised learning, transfer learning, and reinforcement learning. Let's start with the first one. Supervised learning is when you're gonna have the data and the labels. And the algorithm gonna try to predict the label. And if he gets it wrong, he's gonna correct himself until he finds the right label. This act of correction is what is called supervised learning. Now, supervised learning has two main different inverse problems: either classification one or regression one. Classification is when you're gonna try to predict if something is one thing or another. For example, if predicting if someone gonna have heart disease. If it's only two options, we call it binary classification. If it's more than two options, we call it multi-class classification, like detecting or predicting dog breeds. On the other hand, regression is when you're gonna try to predict a number. For example, how much will this house cost based on the number of bedrooms, the area, or how many people will buy this app based on the website, the advertisement, the clicks, the likes. These are the two kind of problems on supervised learning. Now, we're gonna try, I said you're gonna try to run a small demo, live demo, to illustrate this concept of supervised learning using a use case. Again, I don't guarantee anything. I don't promise anything. You know how it goes with the live demos. Let's try to run this and see if it's gonna work. Okay, at least it's doing something. Let's see. All right, perfect. So here we have what we call the Amnis dataset, which is dataset that represent 70,000 images of handwrite of handwriting of digit number, going from 0 to 9 within the labels. So here we have the data, which is the images, and we have the labels, as you can see, for each image. So as you can see, it's supervised thing, and it's multi-class classification problem here. We have 10 classes going from 0 to 9. All right, we're gonna give this algorithm, our machine learning algorithm, this data set with the labels, but we're gonna give him 60,000 images to train and 10,000 to test on it. Let's see how it's gonna perform. So for that, okay. All right, we have our application. For that, we're gonna train our model. So if you remember, I've been talking about the epochs. This is the kind of epochs, which means going through the whole data in order to train. You can see that there is also a batch thing, which is normal because we have 60,000 images and it can't fit in my memory because I'm running this locally. So I'm creating subset to go through the whole data. That's all. And you can see I'm running this for 5 epochs, and we already get very good results, as you can see, 98%, 98% accuracy. So here what you need to know, just for the moment, for the training accuracy and validation, we need something very high. This is what we are looking for. And for the loss function, we need something very low. This is it. You don't need to care about this for the moment. And here, that our model has finished training, let's try to run it on some test data set. So now, if I test it on on an image that it hasn't seen before, it gives very good results. You see, it's correct. He predicted the label, predicted the class. He's showing that it's equal to 1. If we test it again, you can see that it's 9 now. Again, yeah, it's performing very well. You see, this is data that it hasn't seen before. He wasn't trained on this. Now, we can take this step further, but again, I don't know how the model gonna perform, but let's try it this time on my own handwriting style. Let's see how we're gonna perform. Let's try with maybe 3. Okay, it's doing well. Even for my handwriting style, which is never seen, is able to be predicting this. So it means that our model is almost general, very good one. Let's try with another one, like 5. Okay, he got it with the confidence. As usual, he give you the probability. It's 0.8, it means the probability of it's 5. If I'm trying something like 7, here, you get it wrong. You see? You predicted that it's 3. I know that's my handwriting style. If you see with 4, for example, okay, he got it wrong. You get it right. So you can see, our model is very general here. So this is just a small example, a use case to illustrate the supervised learning. We have the data, we have the label, we put our model to train on it, and then test it on something that it hasn't seen before. All right, let's close this. Let's go to the next problem, which is unsupervised learning. Now, imagine you have the purchase history of all your customers at your store, and the marketing team is asking you to send a promotion for the summer. Now, you know that not everyone is going to be interested on this, right? So you decide to run a machine learning model on your data, a clustering one, by the way, which is going to try to group all the people that purchase similar thing. And you're going to find there are 2 different kinds of groups. People who purchase only on the summer and people who purchase only in the winter. So now you can target only the people who purchase on the summer for the promotion. What I mean here is that for the unsupervised learning, we're going to have the data, but we don't have the labels. And it's the machine learning model who's going to predict the labels. Let's see an example of a use case to illustrate this. Let's run, again, a small live demo. Again, it's running locally, so if it crashed, okay, it's given us some results. So here, as you can see, me explain. Now we have different kind of data. We call this the iris dataset. It's representing three species of flowers, Setosa, Verticolor, and Virginica, with 50 samples for each class. And for each flower, we have 4 parameters, which is the sepal width and length, and the petal width and length. And you can see that these 3 different classes, that one, it's easy to predict it, this one. You can see it's linearly separable from this. It's easy to predict this class. But this one, these 2 are challenging. What you're gonna do now is to give our machine learning model this data, but without the labels, of course. We want our model to predict this. This is the idea of unsupervised learning. So the first thing that he's gonna do, of course, we have 4 parameters for each sample. You're gonna do some dimensional tree reduction, maybe PCA, principal composite analysis, in order to make it only 2-dimensional. And then we're gonna run some clustering algorithm like k-means. And let's see how we're gonna perform. Okay, all right. He gave us the results. This is the prediction of our algorithm without knowing anything about the labels. And if you compare it to our result, so in the right here, we have the actual result, so we know it. And we have the prediction. You can see that this one was easy to predict, but this one was challenging. And I agree, like even for us, we can separate this. So it's for the machine learning, it's gonna be very hard also. But this is the kind of stuff that unsupervised learning is doing, is trying to predict the labels without having any kind of information about it. And here the k-means, just to give you an idea, you're gonna start with a value, and then you're gonna calculate the mean of the cluster. Each time you're gonna classify, like, put each sample with an Euclidean distance or the minimal distance between this and the one that he chose, and do the clustering and calculate again and again the mean based on this. This is a sample example. Here you can see the different steps. Let's see. Yeah, you can see the step 1, step 2, step 3, how he's able to classify. All right. So this is the unsupervised learning. Let's move to the next one. Let me stop the demo. Transfer learning. Now, transfer learning is when you're going to use what model has already learned in one domain in order to help you on another domain. For example, if you want to predict from this image the dog breeds, you're going to use what already pre-trained model has done with the different car types, who know how to differentiate different car types, and then adapt it and tune it for your own problem. Now, why is it valuable? Because when you're going to start doing machine learning and training different models, you're going to see that it's an expensive task. Each model going to do 1 million of calculation. And sometimes these calculations aren't free. You need to pay for that. So instead of going from scratch and learning what an image is and what patterns in the image, you're going to use what already another model has already done and tune it and adapt it for your own problem. It's going to save you a lot in money and in time. This is why it's important to do this. Let's see an example. Here, we're going to take the famous examples, which is dogs versus cats, of course. So again, here, notice something. This time, we are not using, like before, 70,000 or images to train the model. We're using only almost 2,000. 1,000 for each class, for dogs and cats, and only 72 to test. So as you can see, it's not big data here. We have a small subset, which is nothing, 2,000 images. So the idea how to create a model, a robust model to predict this if it's dogs or cat, is to use what already another pre-trained model. In our case here, it's called VGG16, and this model was trained on a huge dataset. It's called ImageNet that differentiate different many classes. And you're gonna try to train it on our 2000 images. Again, you're gonna have the epochs, but here we're gonna use only 5 epochs. And you're gonna see that only 5 epochs, which is nothing, 5 epochs, you're gonna see how he's gonna perform just by running this using a pre-trained model to predict. So again, he's doing the batch size to go through the different images, the whole data. Let's see. Okay, not something here. From the first epoch, we were able to get a performance of 90% accuracy, which is amazing. You see, just by using a small subset, but again, a pre-trained model on this subset, it gives you from the first epoch something amazing, which is very important, like valuable. This is why transfer learning is amazing. So here you're gonna finish the 5 epochs. Okay, he's doing pretty good. 95% accuracy, okay. Let's see, all right, okay. Now you can always get the 2 curves that I showed you earlier, the training and the loss validation here. But now let's try to predict on images that it hasn't seen before. We have 90% accuracy, so. And you can see we have 15 images. He gets wrong only on one case, this one. You see, he predicted dogs, but it's cat. So you can see how it's very powerful, the transfer learning, just by using a subset. But pre-trained model on this, he was able to train very well and get very high results. Let me close this. Let's try to another samples of images, how you're gonna perform. Okay, now, this time he got 2 wrong. But again, we have an accuracy of 90%. This is why it's getting wrong. But we have very good results just by training it for a small subset and 5 epochs, which is nothing. So this is why it's amazing. All right, let's see. Let's close this. Let me close demo. Let's see the final problem, reinforcement learning. Reinforcement learning is when a model gonna do some action and you're gonna punish it for doing it bad and rewarding it for doing it good. A good example of this is to teach a machine learning model how to play chess or the game Go. So the most very known one and the best till now is the one provided by DeepMind AlphaGo. And this kind of problem is very used for video games. Let's try to run an example. Here, I created a small game, which is a maze game. And I'm giving my agent, we call this an agent, some rewards, some negative rewards, and positive one, as you can see here in the red. It's negative and positive. I'm telling him, find the right way and the right path in order to get to the goal. And he's learning by himself. You can see it. I don't know if it's gonna converge or not. Is he gonna be able to find the right way? It's running locally, but this is the idea. You can see it. It's running, you give him some rewards. I gave him 500 episodes, which means 500 games each time, and I'm changing the parameters each time to find the right path by giving him some rewards, negative and positive. Changing the parameters. Let's see if he's gonna converge for 500 episodes. You can see, he got it. He got it. Now he knows how to resolve the maze game. You see, this is reinforcement learning. Now he's converged and he learned the optimal path each time he's able to find the solution. This is the kind of demo to illustrate the reinforcement learning. Again, it's very used for video games, but also for robotics, like to teach a robot how to walk, for example. All right, now we have finished with this. We have seen some use cases for each one. So now we know how to match our business problem to machine learning run, right? If it's supervised learning, I know my inputs and outputs. And supervised learning, I'm not sure what of the output, but I have the input. Finally, transfer learning, I think my problem may be similar to something else. All right, let's move to the next step. Data. Data. What kind of data do we have? And here, data comes in many different shapes and size. But the main two types are either structured one or unstructured. Structured is like CSV files, Excel files, tables, data frame. Unstructured are like images, audio file, text like emails. Now these two kind of type of data can be either static or streaming. Static, it means that it's not going to change over time. Like if you take a data frame or CSV files of medical patient records, it's going to be static. And the more data do we have, the better. Streaming, on the other hand, is when the data is going to change over time always. Like, for example, stock market price or time series data of dioxide carbon. And this kind of data is used for doing some monitoring and forecasting. Now, this is a common data science workflow. You're going to have some static data, for example, here, a CSV file. You're going to try to create the environment using Anaconda, and then using some libraries to convert this CSV to a data frame, like a Panda. Then you're going to do some data analysis using Matplotlib, for example. And finally, building a machine learning model who's going to, for example, predict if someone's going to have a heart disease or not. And finally, you're going to share this or create an application for it in this form. You have the heart disease prediction app, for example. You're going to upload your CSV file here, as you can see. You have the heart disease CSV, the data frame. Next step is to doing some data cleaning. Maybe removing duplicates, handle missing value, encoding. As you can see here, it's going to give you a clean data cleaned successfully. Next, you're going to choose machine learning model, maybe a regression one, random forest, support vector machine. You're going to play with the different parameters of each model. And then you're going to train it. Turns out, it gives you very good accuracy, 90%. The model was very good, trained very well, and you're going to have some graphs on that. Next step is the prediction. Now you're going to have some new patient with different parameters, and you can make now with the trained model the prediction. For example, here, the probability of having heart disease is 76% using this parameter of the patient. Now, again, you can play with different parameters of the new patient, and it's going to predict something using the trained model. For example, here it's negative. He has the probability of heart disease is 22%. What I mean here is this is the kind of application that you can create based on the data science workflow that you have seen. All right. Let's move to the next step, evaluation. What defines success for us? And what metric are we going to use to measure the performance of our model? So here, when you're going to start a new project, you need to fix a goal first. For example, for this project to be worth pursuing further, we need a machine learning model with over 99% accuracy. If you take this example, 97, it's not worth pursuing. We need to change the model. Same thing for classifying car insurance claims. Is it fault or not? If it's under 95, you need to change. What I mean here is that each time you're going to start a project, you need to fix a goal. And these are the different metrics that you're going to use for different problems. Like classification one, you're going to use accuracy, precision, recall, confusion matrix. For the regression problems, we're going to use mean absolute error, mean squared error, RMSE, and the R2 scores. Okay. Features. What do we already know about the data? Now, features means different forms of the data. If you take the previous examples of medical patient records, you want to build a machine learning model on this. The idea is what? It's going to be to use these parameters like the weight, sex, heart rate, chest pain, in order to predict the heart disease colon, if he's going to get sick or not. These parameters are called feature variable. The one that we want to predict, it's called the target variable. Now, these features can be either numerical, like the weight, heart rate, chest pain, or categorical, like the sex, male or female, heart disease, yes or no. Now, sometimes you're going to find what we call derived features, which means you are the one who's going to create this based on your own data. We call this feature engineering, looking at different features of the data and creating a new one. Now again, these features are related to the structured data. But unstructured data has also features. Imagine you have a couple of images of dogs. You run a machine learning model on them. You're going to start detecting some shapes, 4 legs, 2 eyes. These are going to be the features that are going to be used by the machine learning model to resolve some computer vision model, like doing object detection or pattern recognition. Now, what features should you use? Here, try always to get the features that cover the whole samples, all your samples. If we look at this one, these features, the most eaten food, it's cover only 10% of the samples. This is a bad feature. Don't use it. It's going to give you a bad model. Try always to get the features that cover all your samples, or at least 80%, and then we're going to see how to deal with the missing value. OK. Modeling part. Here, I break it down in 4 main parts. Let's start with the first one, which is the most important concept in machine learning. We call this the 3 set. Or other word, the training, validation, and test split. Now, when you're going to start doing some machine learning, you want your model to perform very well on real new data. For that, you need to split your data into the training split, where you're going to train your model on, a validation split, when you're going to tune it and improve it, and finally, a test split when you're going to compare on it. Now, why is it important? Think of it like this. You are students, you want to learn new subject, maybe a course on AI. You're going to start by doing the course materials, right? This is going to correspond to us to the training set. Then you want to practice, and test yourself on some practice exam. This is going to correspond to us to the validation set. And finally, you're going to pass the final leg test. This is going to correspond to us to the test set. Now, if a student gets a good score or good grade, it means that he learns the subject, right? He knows what he's doing. This act of adaptation in machine learning is called generalization. The ability of machine learning model to perform very well on data it hasn't seen before. This is exactly what you are looking for. We're looking for generalization. Because imagine there is a leak of the final exam. The professor gave them the final exam. Everyone gonna get a good score, right? But did they really learn something? Probably not. Probably just memorization. This is exactly what we want to avoid when doing machine learning. We want to avoid memorization. We want our model to be general. This is very important. So again, we're going to see that here that's called overfitting, but this is very important. OK, now this is a small example how we can do it with 100 patient records, for example. In general, we take for the training 70–80%. For the validation, 10, and test 10–15%. It depends. OK. Now, each part is going to correspond to us to do something. First one is to choose and train the model. Validation data is to tune the model. And finally, the test data to do some model comparison. Let's start with the first one. How, based on our problem, what model should we use? Here, it's not a rule. It's an advice by experience. It's not a rule again. In general, when you are working with structured data, machine models like decision trees, like random forest, XGBoost, tend to be working the best. And if you are working with unstructured data, like images, audio files, deep learning and transfer learning tends to be working the best. Again, it's not a rule, it's by experience, and you can take it as a start point. You can start within it. OK, now that you have chosen our model, Next step is to train it, right? If you take the previous examples of medical patient records, the idea is to take these parameters and build machine learning on this in order to predict this. We call this X. And the label that we want to predict, we call it Y. Now, machine learning model, when you're going to try to train, what it's going to do is trying to create a relationship between this Y and X in the form of Y equal H of X. So here, H is going to represent our model. And each model has its own way of doing it. Maybe it's a linear model, polynomial, non-linear. It depends on the problem that you are working on. If you take a small example of regression problem, you can see that the hypothesis here, which is going to correspond to our model, h of x, going to be equal to a linear function, which is theta 0 plus theta 1x, where theta 0 and theta 1 are representing the parameters of our model. And then we're going to fix what we call a cost function. Here it's equal to the mean squared error between the true value and the predicted. And the idea is when a model going to train is try to minimize this cost function based on these two parameters by updating it. You can use different optimization methods like descent, gradient descent, for example, here. But this is the goal when he's trying to train. Again, you can see it here. In blue, we have the true value, the observed value, and the red, our model. And you're going to try to minimize this error between the predicted and the observed. Again, this is just to give you an idea. Don't think about it. We don't care about it now for the moment. Your goal of you is to try to minimize time between experiments. This is very important. When you're going to do a lot of machine learning and train a lot of different models, it's going to take a lot of time. So 2 tips for this. Never start with the whole data. Start always with a subset. If you have 100,000 subset samples, start with 10,000. Never start with the whole data. Second tips, start always with simple model and then add some complexity. And it's going to save you a lot of time and you can test a lot of different models. This is very important. So things to remember, some models work better than others on different problems, of course. Don't be afraid to try things. It's not going to cost you anything. Try. As long as you follow the 2 tips, right? Start small and build up, add complexity as you need, of course. Okay, now that you have trained or choose a model and train it, next step is to tune it, to improve it. If you take the previous examples, if you remember the chicken, you can see that cooking the chicken for 4 hours at 300 degrees is not as good as doing it for 1 hour, 200 degrees. This is how you can tune the oven. Same thing for machine learning models. The machine learning models have hyperparameters, parameters that you can play with it, adjust it, change it to get a better model. So if we take a random forest, for example, algorithm, you can see that the number of trees is considered as parameter, and you can increase it to add some complexity. Same for the neural networks. The hidden layers is considered as hyperparameter that you can add another one to add some complexity. This is the idea of how you can tune your model in order to get a better model. So things to remember, machine learning models have hyperparameters that you can adjust. A model first results aren't it last, for sure. And tuning can take place on training or validation dataset. It will depend on the size of your dataset. If you have a small dataset, you can do the tuning on the training one. All right, next one is model comparison. How will our model perform in real world? Here, when you're going to finish training your model and tune it, you want to test it on your real data. Here you're going to face 2 cases. First one is when your model is doing very bad on the training and on the test. Second case is when your model is going to do very good on the training and very bad on the test. What we are looking for is the third case, where our model is going to do very well on the training and very well on the test. Now these 2 kind of scenarios, 2 cases, are known under the name of underfitting and overfitting. And this is an example of it, as you can see here. What you are looking for is this second column, the optimal fitting. Now, there are many several reasons why this happens for the overfitting and the underfitting. But the 2 main common ones are either data leakage or data mismatch. Data leakage, it's same thing as the previous example. Remember? We have a leak of our final exam. So there is a leak from our test data into the training. And you want to avoid at all costs leak from the test data into our training data. This is very important to avoid the overfitting and the memorization. Data mismatch is when you're going to train on some kind of data and then test it on different kind of data. It happens also when you are not training your model for a long period. Now, I put you here some advice how you can fix this. For the underfitting, you can try more advanced model, increase the model hyperparameters, reduce amount of features, train for longer. And for the overfitting, collect more data and try less advanced model. Okay, now we fixed these two problems. Next step is to compare different models, right? Here, it will depend on the goal that you have set. Imagine you are looking only for the best performance. You don't care about the time that's gonna take you to get the best performance. The third model is gonna be the best for you, right? Now imagine you are working on real-time data. You want something for computer vision. A very small prediction time. The first one is gonna be the best for you. Now you want something between these two, a compromise. The second one is gonna be the best for you. What I mean here is that it's not always the model with the best performance, the best model. It will depend on the goal that you are working on. It depends on the goal that you have set and the problem that you are working on. This is the idea. So again, things to remember, want to avoid overfitting and underfitting, of course. Keep the test set separate at all costs. Compare apples to apples, of course. Train on the same kind of data and test on the same kind of data. And one best performance metric doesn't equal the best model. Okay, experimentation. Now you know all these steps. You're gonna start doing it, going through these all steps, and then you're gonna see that it's an iterative process. Why? You're gonna start doing something, build a model, it's give you bad results. Try another one, good results. Another one, perfect one. What I mean here is that sometimes when you're gonna start working on your own data, you're gonna face some problems that you didn't expect, and you need to resolve it by yourself. This is why experimentation is very important. You need to experiment by yourself. It's always the case. Experimentation has very high weight in machine learning. So, okay, now we have our framework. We need to build it. For that, we need to match it to some data science and machine learning tools. For that, we're gonna have our computer. Then we're gonna create the environment of the data science environment using Anaconda. And then you're gonna use some libraries to build this environment. And each library corresponds to split in our framework. You can see that the data science here part, it's built using Anaconda and Jupyter Notebooks, for example. The data analysis, you're gonna use some Panda, Matplotlib, NumPy. And for the machine learning part, we have these libraries, TensorFlow, PyTorch, scikit-learn. In our case here, today we're gonna be focusing on scikit-learn. Why? It's built in Python, of course. It has many inbuilt machine learning models. We have a lot of methods to evaluate our machine model built in, and it's a very well-designed API. We'll be focusing on scikit-learn. And this is the scikit-learn workflow that we're gonna go through using Jupyter Notebooks. We're gonna get first our data ready, which means data cleaning, data wrangling. As I always say, data is the nutrition of AI. If you give AI junk food, it's not gonna perform well. So data, cleaning the data is very important. We need to have a very good quality of the data. Then we're gonna pick a model that suits our problem, of course, fit it, which means train it, and make some prediction, evaluate our model, improve it through some experimentation, and finally save it. Quick side, I made this course in Arabic also. I'm talking to the Arabic audience in YouTube because we are streaming. So again, you can go to my GitHub and you're gonna find the Jupyter notebooks exactly the same in Arabic. And you can follow in our YouTube channel. I made 2 videos on this in Arabic, the same workshop. And you can follow this with me, along with me, and code with me, and you're gonna do it in Arabic also. Okay, some tips here. Always ask in Stack Overflow, read the documentation, and you can follow with me with the code. Now, before we finish, I have small game. Let's play a small game. Again, let me run this. Okay. Don't be afraid. It's anonymous. You can put whatever you want as a nickname. It's nothing. Let's start by a small tutorial. You can use either your phone or your computer, as you wish. Let's start with a small tutorial of this. You can join this game just by going to kahoot.it and put this code pin. And then put wherever you want as a nickname. It's anonymous. It's nothing. Don't be afraid. And if you don't play, we can switch it as you wish. Let's see if some people are gonna join. We're gonna start with a small tutorial, just to know how to play the game. You have some people joining. For the viewers on YouTube, you can also join. You can do it. Check. Okay, wait a few minutes. All right. Can we start or just wait again? 45 people, okay. All right, we can start, I think. Still. Okay, still. 48. So again, we're gonna start with a small tutorial. I have 3 question quiz, true or false, or puzzle, just to know how to play the game. And then we're gonna move to the things. So I think we can start. Okay. Okay, let's start. Okay, so here, you're gonna have some question, different colors, and you're gonna choose. For example, here, true or false? 2 by 2 is equal to 3. If it's true, you click on the blue color. If it's false, you click on the red, right? Okay. Just to understand the mechanism of the game. And we have the time in the left. So we have 40 answers. The time is 8:07. Okay. All right. That's scary. The 4 people. Guys, it's anonymous, but come on. Okay, we can move. Next question. Here, I need you to know that there is a rating. Again, just to understand, the score is based on the right answer, but also the speed. The fastest gonna have the maximum score. Okay, you start getting it. Let's go to the next one. Puzzle. Puzzle. Arrange the numbers from the smallest to the largest. You start from the bottom and go. Sorry. you can do it like from there. It's same. Okay. My answer 40, 41. Okay. Let's see how many people are gonna get the right answer. Ah, 10 people. Okay. I understand it's tricky one. But again, you get it. You start from the bottom and then until the this is the idea. Okay. This is tutorials again. We are learning the mechanism of the game. Let's see the final question, the quiz. 1 plus 1 equal 2, 5, 10, 80. Guys, I trust you. Come on. I don't wanna wrong answer on this. Let's see. Okay, 49. Okay. Ah. Scary. The one here and the one here. I hope it's from YouTube, right? It's not here. Okay. Now you get it. So we have a podium. Let's see. The first one. We have ML3. AK. First one. Okay, let's see. Slum. Okay, okay. I hope it's here. It's not on YouTube. Okay, let's start the real quiz. Now you know how to play the game. Let's try. It's gonna be the same thing. You need to join and let's start the AI machine learning course. Let's see if you are really listening to what I was saying or not. Okay, you can do exactly the same thing. Okay, 45, we were at 49, I think. Okay, 7. Start. Should have put a price at the end to make it more competitive. I will think about it next time. Okay. People joining, 48. We start? Okay. I think 48 is good. I think everyone joined. Let's start. Here, I put you 20 questions again, just to be clear. 20 questions. Let's try to see how it goes. What is machine learning? Is it an operating system, programming language, a type of hardware, or a method to teach computers to learn patterns from the data? You have seen this. Okay, 5, 4, 3, 2, 1. Okay, good. Yeah, great. 45 people, only one said it's programming language. Okay, let's move to the next one. Great. Sloan is on the top. Okay, let's see how it goes. Again, rapidity, speed, and the right answer to get the best score. Let's move, let's see. We have seen it, just to give you a reminder. To learn patterns in the data. The puzzle one. This is arrange the following steps in the correct order for typical machine learning projects. You remember? Data collection, data modeling, model deployment. From the bottom to the top. Okay, 42 answer. 47. Missing 2 people. Four, 3, 2, 1. Okay. You see? 21 got the right answer. 29 got the fourth. Okay. Okay. Let's see. Sloan is still in the number 1. I don't know who he is, but it's good for the moment. Okay. Which of the following is a type of machine learning? We have seen this. Supervised learning, unsupervised learning, reinforcement learning, all of the above. Remember, we made some demos on this, so you should remember. Okay, 2, 1. Okay. We got only 2, 3 wrong. Okay, all of the above. Perfect. Let's see. Tomboy making some. Okay. What does the term overfitting refer to in machine learning? This hard one. It's the model that is too simple, a model that performs well on new data, a model that cannot learn from the data, and a model that performs well on the training, but poorly on new data. Okay, this one was hard. Okay, it's a model that performs well on the training data, but poorly on new data. We have seen this, the memorization thing. It's performed very well on training data. Okay, let's see. You see, I told you, we have some comeback here. Everything is possible. Don't try. Okay, it changed everything. Let's see. We are at the question 6. We have time, don't worry. You can make a comeback. What is the purpose of validation set in machine learning? To tune a model's hyperparameters to train, to test, or to store the model. Okay. Three seconds, 2 seconds. All right. Okay. More of people were thinking it's to test the model. The test split is to test the model, validation to tune it. Okay, let's see the results. How it goes. You see, noticed on the top. Okay. Let's move. Which library is commonly used for machine learning in Python? We've seen this at the last slide. Panda, NumPy, Matplotlib, or scikit-learn? Okay, 10 seconds. Okay, 27. Okay, there are people listening. It's okay. I'm fine with it. 27 is okay. So we have again slow. Okay, coming back. Let's see. What is unsupervised learning? Learning from expert knowledge, learning with labeled data, learning without labeled data, and learning with rewards and punishment. Remember the class train one, the iris data, flowers. Let's see. 6 seconds, 5, 4. Okay. Almost perfect. 42. This is great. Okay. It's taking the lead. What is supervised learning now? It's learning with labeled data, with reward and punishment, from expert knowledge, or without labeled data. This one is easy. Should have it. Hope. Let's see. 9, 8, 5, 4, 3, 2, 1. Okay, let's see. Almost perfect. You see, 2 people. I don't know if it's here or YouTube. We're gonna say YouTube. Okay, let's do. It's not like it's taking the lead. Let's see, 10 question. What is now the main goal of classification algorithm? To divide data into distant categories, to predict continuous value, to optimize a reward signal, or to cluster similar data point together. Classification. Okay. Okay, 29. This was hard. So to divide into different categories, distinct categories. This is the classification problem. What is this? Okay, now you change Tomboy. Number 1. Okay, let's see. In machine learning, what is feature? The algorithm used for training, the error rate, the output, or the input variable used to make prediction. Remember medical patient records, the parameters? These are the features. Okay, good. The input variable used to make the prediction. That's right. Okay, this is good. We have some competition here. What is the primary objective of a regression analysis? to classify data into categories, to reduce the number of features, to identify clusters, or to predict a continuous outcome. Okay, to predict a number, that's right. See the rating, scoreboard, okay. 13, so what is model in machine learning? An algorithm that makes prediction or decisions based on data, a data set used for training, a method to pre-process data, or a type of software. See. This is an easy one. Okay, we have 6 people and 4, okay, 10 people. It's an algorithm to make prediction or decision based on the data. Okay, Noah is doing very good. He wasn't in the top 5. Let's see. What is the primary purpose of a test set this time in machine learning? To train, to pre-process, to tune, or to evaluate the performance of the trained model? I should remember to split the 3 set. Okay, let's see. 40 answers, 2, 3, 2 seconds. Okay, to evaluate the performance of the trained model. Let's see. Ah, you see, I told you, Noah is doing really good. He's doing a comeback here. 15. Overfitting occurs when a model performs well on the train, but poorly on the test. True or false? Okay, it's true. Oh, we lost it. Okay, Tomboy is still number 1. It's the 16. Supervised learning requires labeled data to train the model. True or false? Even if you are not sure, random, just click. You're gonna get some score maybe. You see, there are a lot of people that didn't answer, just click. Okay, we have 39 answers, true answers, true, it's true. We are arriving at the last questions. Tomboy still, okay. Maybe you're gonna have some comeback. In unsupervised learning, the algorithm is provided with labeled output data. True or false? Okay, 15 viewers, okay. See the results, false. T, okay. Maybe T can do it. In machine learning, features are the input variables used by a model to make prediction. True or false? Okay, it's true. You have seen this. He's keeping, but it's very close. Be careful. So the test set should never be used during the training phase of the model development. True or false? Okay, it's true. Now, still have 1 or 2 questions. We are at 19, I think. Yeah, the last question, true or false? The accuracy metric is often used to evaluate the classification model. True or false? Let's see if you can make it. if you're gonna do a comeback or not. Okay. It's true. Let's see the podium. T, you can applaud him. Third, Hamilton through. And the final one, who is? Okay, let's see. Is there suspense or Tomboy? Okay, congrats. I don't know if it's here or on YouTube, or congratulations. I should have put some prices on this. But yeah, great. This is very good. Now we can, let me just go here. Okay, thank you all. I hope you enjoy it and learned at least something. Now, let's start modeling. But before this, we're gonna take a small break, of course, 10, 15 minutes. And if you can give a feedback, it's gonna be very good. Thank you, guys. Thank you. We're gonna be back in 10, 15 minutes. You are the tomboy. You should have put your true name there. No, maybe next time. Thank you. Okay, so here you should go to my GitHub account. I don't know if you have access to it. It's here, you can see it. This is my username, Halimi. Tell me if everyone is there. You can either get into the class hub, which is Jupyter Notebooks, and you're gonna have all the materials and you're gonna follow with me with the codes, or just follow just by watching me doing these steps, and you can practice again by yourself, for sure. I put you all the materials there. So go to my GitHub account, then you're gonna find all the materials, but to make it easy, I put you here. You need to create a GitHub account, or if you don't have one, go here, sign into it, and go to this link. It's gonna add you to a list to get access to the class hub, which is Jupyter Notebook. So you put your GitHub ID, submit the form, and you should have access to the binder class hub. And then you go to the class hub binder. You're gonna have this page, and you click on Jupyter Hub. And it should send you to here, to something like this. Try it, tell me. For the viewers on YouTube, you can always use Google Collaboratory. It's the same thing, and did do a git clone of my repository. But this is for cost people. Again, go to my GitHub, create a GitHub account if you don't have it. Go to this link to add your GitHub ID, and then go to Class Hub Binder and click on Jupyter Hub. When you are there, you'll be here. It's gonna be like this. And you need to go to Introduction to Machine Learning and select the Introduction to Machine Learning. Okay for you? Again, you can do it, follow with me, or just watch what I'm doing. It's the same thing. Okay, let's start. So just to give you an idea, this is Jupyter Notebook. In order to run a cell, either you can click here on the play to run it, or on Shift and Enter. You can choose. And then if you want any information about any library or function, Shift and Tab. And it's going to give you the definition of the function and the different parameters. Okay? This is the idea. Again, just before I forget, for any question, you can go here into the Etherpad, and you can put your question to my colleague. Didier gonna answer you. Sorry, what?
How can I reach to your account?
The GitHub one. Go to GitHub and put my name.
I'm in GitHub, so I should search or
Yes, search and put my name, A-Halimi, and go to username, and you'll find me. And find this repository, Introduction to AI. Halimi. And go to the repository, Introduction to AI workshop. And you're gonna find the whole materials. If you are lost, you can always go to our YouTube channel, the last video, this one. And I put the link here of the GitHub for the workshop groups. I think it's easy for you. Just click here on the YouTube channel. The last one. So for any question, you can go to the Etherpad and put wherever you want. My colleague gonna be answering. All right. I think we can start. Just put this like this. It's okay for you? Here, what you're gonna try to do is going through these different steps that you have already seen, right? The idea is to get first the data ready. So we're gonna do some data cleaning. Then we're gonna choose the right model that match our problem, fit it, which means train it, evaluate it, improve it through doing some hyperparameter tuning, saving it, and load it again. And finally, we're gonna put all the things together in order to get a pipeline or framework. Again, in order to run a cell, either you click on play or shift and enter. If you want any information about the function library, you go here and do shift and tab. It's gonna give you all the thing. Okay, Let's start. So here we're gonna import some libraries, the one that you have seen, matplotlib, numpy, panda. And the first thing, we're gonna try to work on the heart disease CSV files. So here, the idea, in order to get the data ready, or doing some, we call this data wrangling, there are three main steps. First one is splitting the data into, of course, X and Y, features, labels. Next step is converting non-numerical value to numerical value. We call this the feature encoding. You remember the categorical features? We need to convert them into numbers. And the last one is the filling the missing value. We call this imputing. Here, for the heart disease CSV file, you can see that the attribute of the file, again, you can find all the data and all these stuffs in the GitHub repository. You can have all this. So you can practice by yourself again. These attributes, the age of the individual, sex is the male or female, chest pain, all these parameters. For that, we're gonna read our CSV files using some libraries like Panda. We're gonna have this data frame. Again here, just to be clear, you remember, this is gonna be age, sex, CP, the parameters that we're gonna use. This is gonna be the features. And the colon target is the prediction, heart disease. 1 for heart disease, he has the heart disease. 0, he has not a heart disease. It indicates if it's disease or not. This is the one that we wanna predict using these parameters. So the first step, as I said, is to split the data. Of course, we need some X and Y. For that, we're gonna drop the target column like this. Heart disease dot drop, and we drop the target one. So here we have our X, the features. And we're gonna put Y equal to the heart disease, the target column that we wanna predict. And that's how we can split our data, right? X and Y. Then, now that you have our X and Y, we can use some libraries like scikit-learn, a function called train test split, to split our data into a training and test. Here, as you can see, we are putting our test data equal to 20%. So it's gonna split our data into 80% for the training and 20 for the test, as you can see here. And we can check this by doing X shape, which is here 302 samples. This is the samples, number of the samples that we have in the data. Multiply by 80%, it gives you the 242. So it did well, the splitting. Okay, now we know how to split our data into X, Y, and again, using some function, we can split it into the train test and X, the train and test. Let's move to the next one. Let's try to make sure it's all numerical. Here we're gonna use another data set, for example. We call this the care sales data set. It has this attribute, the brand, which is make here, the brand of the car, maybe Honda, Toyota, BMW, the color, the odometer, so the distance, the doors, and the price. So here it's a regression problem, right? You are trying to predict the price, a number. For that, you can see that if you look to the data frame, this is how it looks. And you can see that we have two columns, make and color, which are categorical here. It's not a number, it's string. If you go directly onto this and you look to the D type, you can see that the make and the color are object, which is string here in our case, and the others are numbers, integer. If we build our model directly, for example, we have our X, which is, we're gonna drop the price column, as we did before. We're gonna drop this column in order to get only the features, X, and we're gonna put our Y equal to car sales price. And we're gonna split our data, again, for the training 80%, for the test 20. And let's be direct, try to build a random forest on this. Let's try to make it work directly from this, without doing anything. You're gonna see that let me run this. It's gonna give you an error, which is normal because couldn't convert string Toyota into a number. Here you need to know that this doesn't work because you have to convert it into numbers. Models doesn't understand the categorical features. We need to convert them then first. So again, let's look to our data set. You can see that it's data frame like this. You can take some information about these different columns, the make, which is the brand here. We have 4 categories, which is Toyota, Honda, Nissan, and BMW. For the color, we have 5 categories, white, blue, black, red, and green. It gives you some information. And for the doors column, we have 4, 5, 3. Okay, now we're gonna use what we call a function provided by scikit-learn, which is one-hot encoder, and which gonna allows us to convert these categorical features into numbers. Again, as you can see here, categorical features are make, color. What do you see here? Doors. Why? Why did we put doors here? Doors is a number, right? You can see it here. This is why I told you, like, machine learning is about experimentation. It's not like applying things. Yeah. Here, doors is a tricky one. In reality, okay, I know it's a number, but in reality, it's representing a category. Cars with 3 doors, with 4 doors, and 5. So in reality, it's a category. It's not a number. So we should put it. This is a tricky one. This is why I put you this example. This is why I'm telling you, like, experiment. It's not like applying one. You need to get some insight with the data. So here, this is a tricky one. So we need to put it. Okay, now we're gonna convert it. It's gonna give you some numbers, which is great. We're gonna put it as data frame, and you can see that we were able to convert this from this to this. Okay, now we have more features. Why? The idea is what's going on one-hot encoder, what he's doing. The idea is that he's doing this. Imagine you have the car here and the color. We're going to take only the color. It has 3 categories, red, green, and blue. What hot encoder is doing is taking the color, the 3 categories, and put them like this, red, green, blue. And for the red one, like for the simple one, first car, it's red, right? You're gonna put a 1 for red, and 0 for green, and 0 for blue. Here, second car, it's green. You're gonna put a green, 1 here, and 0 here, and this 0 here. This is what he's doing. This is how he's converting categorical features into numbers. This is why we have more columns, like 12 in our case, because we have seen that we have 4 categories for the brand, 5 categories for the color, and 3 for the doors. All right. So now we know how to convert our categorical features into numbers using one-hot encoding. You can do exactly the same thing. What we did it with scikit-learn, right? With Panda, it handled this. So you can see our car series here, data frame. We're gonna do exactly the same thing, but this time we're gonna put panda.getDummies, and it's gonna do the job for us. But you can see here, okay, it make it clear, as you can see, make BMW, make Honda, make Nissan. You see different categories, the 4 one. Then you have the color black, blue, green, red, and white, and he put 1. So we converted this. It's very easy and very quick. But you should notice something. He didn't convert the doors, right? It's still 454. It's not 001, 010. Why? Because if you look at the type, you can see that the doors is considered as integer here. And the Panda is working only with object type. So for that, in order to resolve this, you just need to convert it to object before doing and calling this function. So remember, you can use scikit-learn or just using Panda, but you need to remember that Panda doesn't read integer. You need to convert it before using it. And now, if we run this, we're going to see that the color now, we have the door 3, 4, and 5, the 3 categories. All right, now that we have converted our categorical features, we can build the train test split, right? You can do it, and we can fit our model on it. And this time, it's going to work. It's going to give you a score, not like before. Before it said that we have some categorical features, some string thing, you cannot do it. But now if we do the model fit and model score, it's working. Okay, now we know how to handle the categorical features. Next step, what if there were missing values? For that, you have 2 different ways to deal with it. Either fill in this missing value with a given value. For example, the mean of the samples of the column. You can take the mean of your samples, or to remove them. But if you remove them, you're going to lose some data sets. So think about it. Either fill in them with a number, which is the mean of the column, for example, or category, if it's categorical features. Maybe you're going to put some missing category, new category. And if it's number, you should take the mean, for example, or remove them. It depends on how you want to work. But if you're going to remove, you're going to lose some data. And data is very important, like, to have when doing this. So if we take this example of the car sales, but this time with some missing value, you can see that this function is going to give us the number of missing value. In the brand column, we have 49, and the others, we have 50 samples missing from the data. Again, when you're going to start machine learning, you need to remember something. Here, as you can see, we have some missing value for the price, which is the column that we want to predict. Here, you should remove them. Why? Because we don't want to get any fake labels, right? We want to work with the ground truth. So these 50 samples, we're going to remove them. Because if we put some missing, we are working with fake labels, which is not good. Should keep our data clean, so ground truth. So the prediction column, always remove the missing value from the prediction that you want to wait. Okay, now, again, to remove this, you're going to do the car sales missing, which is the data frame, drop NA, and you put the column that you want to remove. And put in place true. And here, if you look at, you can see that we remove them. It's 0 now. But we are losing some samples from 1,000 to 950. But it's OK. We don't want to fake labels. We want to work with the ground truth. This is important. So from the prediction, you should remove them when you have missing value. All right, now that we have this, you can create your thing, train and test split. We know how to get to the X. We're going to drop the column price. Then we're going to get our Y, which is the price that we want to predict. Do the training test split on this using 20% for the test and 80% for the training. And now that we have the training and test, another concept, very important. Never, when you split your data into training and test, never impute or fill the missing value for each category separately. What I mean here, you should always fill the training set, and then the result that you get here, you put it in the test set. Why? Because we don't want anything from the test set to interfere into our training set. If we take the test set and put for the missing value some mean, we know that here we are tricking because we need to keep it at almost every time separate the test set from the training. always do your stuff on the training, and the results, put it on the test. We don't want to touch anything from the test, right? I'm losing the server. Let's try if I can get it back. Did I lose the... Okay, I lost my IBEX. Let me call it again. Let me reduce the... Okay. This is IBEX. I don't know if you know how to work with it, but you can use it, the HPC. Let me run the Jupyter notebook again. In your class hub, you shouldn't have this kind of problem. This is related to IBEX. This is why I got. Okay. I have my notebook again. Should be okay. Just quickly. All right, we were there, right? So don't ever use the data from the future, which is the test set here, to fill data from the past, from the training. Because as I told you, we want to keep at all costs the test data separated from the training. So for that, when you're going to fix the missing value, you're going to split your data into training and test. As you can see here, we have our X and Y. We split our data into some training and test, and then we're gonna fill the training, and the result of the one that you're gonna use for the training filling, you're gonna put it in the test. So example here, for this kind of, for the brand, it's categorical feature, right? For that, how are you gonna fill it? It's categorical feature. We're going to create a new one, and we're going to call it missing feature, missing category. And you're going to put exactly the same thing. Here, it doesn't matter. It's missing. It doesn't impact us. So it's OK. For the color, same thing. It's categorical feature. We're going to put a new category, which we're going to call it missing also. And we're going to fill our missing value for the train and test. For the doors, we have categories from 3, 4, and 5. Here we're going to put a number, which is 4 in our case. We took 4. And for the odometer, which is a number here, we're going to fill this missing value by the mean of the column. We're going to take the mean. The new one, the X train and X test, you can see that now it's 0. We know how to fill it, either by numbers, which is the mean, or new category, for example, missing, if it's categorical features. All right, we removed any missing value. Now, you can do exactly the same thing as before. We're going to convert our categorical features into numbers, right? We're going to use one-hot encoder for that. But this time, we filled already the missing. So always start with filling the missing value and then encode the categorical one. This is the process. Now we can encode it. And we can build our new model on this. And it's going to work. We fill our model, missing value. We convert our categorical features. Now we can build our model on this new data. All right. Now you can do exactly the same thing. I'm showing you what I showed you here is using Panda, but you can do exactly the same thing using scikit-learn. Scikit-learn is providing this function called simple imputer, and you can do exactly the same thing. I mean, here I'm just giving you an overview of all you can get. Again, you are the one who's gonna choose the one that you like more. I'm giving you everything. So you can do exactly the same thing, but this time using simple imputer. For that, you're going to create some function. We're going to call it categorical imputer, door imputer, and numerical imputer. For the category, we're going to put strategy constant, and we put missing. For the door, we have already choose to put the number 4, for example. And for the numbers imputer, we're going to choose the strategy mean of the column. And then we're going to choose the categorical features that we're going to apply this function on. For the categorical features, we're going to have make and color. For the door's column. And for the numerical one, odometer. And then you're going to create column transformer that's going to apply these functions on these variables. And it's going to give you the field X train. All right. And based on this, you can create train test and build a model on it. So this is a different way, using scikit-learn or Panda, as you wish. I'm just giving you a whole idea how you can do it. All right, now we can do the categorical feature after we have deal with the missing value. You can convert our categorical features and build our model on it. All right. Now we know how to split our data, know how to deal with category features, how to convert them into a numerical one. We know how to deal with the missing value. There are another steps, which is the scaling, feature scaling, which is always good to have and to apply at the end, which gonna be scale. Here we have two different ways of doing it, either normalization or standardization. Normalization is this rescales all the numerical value between 0 and 1. The standardization, this abstracts the mean value from all the features. Why is it important? Because sometimes you're going to have features like the odometers going from 1 to 100,000 and others going from 0 to 10. So in order to make our model very well and performing very well, we need to scale this at the same level. Because if we want to use the features from 0 to 100,000, maybe you're going to think like, oh, this is very important going from 0 to 1,000. This feature is very important, which is not the case. It depends. And the others going from 0 to 1, you're going to say, okay, this is nothing. This is why we need to scale everything between 0 and 1. This is the idea of scaling, feature scaling. This is very important when you are doing using deep learning models also. So for that, here you have the two functions provided by scikit-learn. You can use either min-max scaler or standard scaler. And you're gonna call it pre-processing min-max scaler, and you're gonna apply it to your X-train, of course, and the X-test. So now we have everything scaled between 0 and 1. Now, I told you that it's very important for deep learning, but random forest feature scaling is usually not required for tree-based models. They can handle this. So it's good to know, always good to know. So decision trees in general, yeah, if you wanna ask a question, go to, sorry? The the cost function? No, it's in the tree. You remember here when I'm doing the fit, it's already there. When you are doing model.fit, there is a parameter that you can set to say maybe you want to just doing this, the cost function using mean absolute error or R2 score. We're going to see it later, but this is the idea. If you have any question, go to you can ask in the Etherpad and my colleague gonna help you. All right. So, okay, I told you decision tree can handle this feature scaling thing, but it's always good to do it. I advise you to do it always. It's good to do the feature scaling. All right. Where we've been, okay, we have the two here. We have already done it. All right, now we know how to do the data cleaning, data wrangling, right? Next step is how you're gonna choose the right algorithm. Here, scikit-learn gives you a map, a cheat map that you can use, and which is very interesting, I find. You can go to their website, by the way, put your here link. Let's see. Oh, I don't. Okay. I put you a link here for their website where you can find this map that you can use. And it's very interesting. Why? It's going to help you a lot when you are beginning in machine learning and you don't know what model are you going to choose. You know how to match your business problem to machine learning problem, right? We have seen this. Is it classification one? Is it regression one? Clustering, dimensionality reduction? You know how to do it. But you don't know what model are you gonna choose, right? Here, as I said, scikit-learn gives you this map, which is very interesting. Let's see how we can use it. If we take the previous examples, for example, a new data set, which is the California housing data set. Let's take a look to it. Okay, this, let me check. Okay, I'm giving some information here. So this is how the data set is looking. We have some parameters like med-inc here, which represent the median income, the house age, median house age, the average number of rooms, the average number of bedrooms, and we have the target. We have the location, latitude, longitude, we have the target, right? The price. This is what you want to predict, the price. But, so again, we know that it's a regression problem, right? We want to predict a number. So at least we know it's a regression problem. If you look at the number of samples, you can see that it's 20,000. Okay, we have an idea. We have 20,000 of samples. If you go there, you have 20,000. We know that it's a regression problem. You're going to start from here. Do we have more than 50 samples? Yes, you go here. Are you predicting a category? No, we're predicting a number. So you go here. Predicting a quantity? Yes. Do you have more than 100K? No, we have 20,000. We have seen this. So it's under 100K. You go here. Few features should be important. You don't know why? I'm not sure. Go here, try ridge regression. Okay, let's try this. It gives us the ridge regression. For that, we're gonna choose the X and Y. You have seen this. We're gonna drop the target. We can build our X and Y, right? Then we're gonna use the train test split to split it into test set and train test. 80% for the training, 20% for the test. And we're gonna call our model. It's called the ridge, which represents the ridge regression, right? It advises us to do this. We're gonna fit it in order to train it in our data, X train, Y train, and we're gonna test it into X test and Y test, right? We train in training split, and we test on the test split. It gives us a score, which is in this case the R2 score. What you need to know is 1 is the perfect score. This is what you need to know. So here it gives us 0.5. It's not that good. I am not satisfied with this. It's not working for me. It advises you to go to ensemble regressor. Here, ensemble regression is another word for multiple models. A random forest is one of them. Ensemble is the random forest, which is very robust and very good. Let's try this one. Scikit-learn give you this, which is called random forest regressor, so you can call it. Do the same thing. Split data, X and Y, X-train and X-test. Call the model this time, which is random forest regressor. Train it on your training data and test it in your test. And this time, let's see, it's gonna give you hope better score. Doing some, okay. All right, 0.8. So before we have 0.5 and now 0.8, which is great. You see how you can improve your thing without doing anything, just changing the model. This is great. I'm satisfied with this result. So this is how you can choose a model for a regression program, right? We can do exactly the same thing, how you can pick a model, but this time for classification one, the heart disease, of course. Let's try to this on heart disease. First thing, look at the number of sample, 300. Okay, let's go. Let's do exactly the same thing. Start. Do you have more than 50 samples? Yes. Predicting category? Yes, this time. Do you have labeled data? Yes, it's supervised learning this time, the heart disease, CSV. We have the labeled data. Is it under 100K? Yes, we have only 300 samples. He advises you to choose the linear SVC, which is the super vector machine. All right, let's try it. For that, Scikit-learn also provide this kind of models. For that, you can, same thing, X and Y, X-train, X-test. We call our model the linear SVC, which is super vector machine. We train it on the train set, and we test it on the test set. Let's see how it performs. Okay, not that good. 0.47, which means 50% accuracy. What does it mean? It's exactly the same thing, as good as guessing. He's guessing 50%. Yeah, you're gonna have hard disease. No, it's just guessing. This is not correct. This is not good at all. All right, I'm not satisfied. Not working. You go here. Is it text data? No. All right, he advised you, K-neighbor. I don't like it. I'm going directly to the last one, which is, we have already seen, the ensemble. You remember the rule that it's not a rule, just an experience. The decision trees and all these stuffs are working very good with structured data. All right, now, exactly the same thing. We're gonna use the random forest. But this time, Scikit-learn proposed also random forest for the classifier. We call this random forest classifier. Before it was random forest regressor, and now a classifier. Okay, let's run it. You see, perfect, 85% accuracy, which is very good, amazing. Now we have a good score. Now I'm satisfied with this. So again, there are tons of models. You can always go to the documentation. I'm not gonna be entering into the details here. Just giving you an overview, an idea how you can search by yourself. So go always to the documentation of the Scikit-learn library. You're gonna find a lot of different models. By the way, you can see it here. If you go here, you see for each category, supervised and supervised, you have tons of models that you can try and see. It gives you how you can implement this. All right. Let's continue. Now we know how to choose a model, how to fit it, how to train it. We already did it. We have seen this. To do this, we have, again, the data, which is the features here, X and Y. And to train, I told you, each model has its own way of training. Each model has its own way. But again, how we do it? By doing this, the fit. The fit gonna train our model into the X train and the Y train. Again, we are working with supervised learning. This is why we have the Y train and X train. This is why. We have the data and the labels. All right. So here, when we do this, he's doing the thing that I was talking about in the presentation, if you remember, trying to create some relationship between the x and the y. And each model has its own way of doing it. And to optimize this, he's gonna use maybe an optimization method like the gradient descent. But in your case, don't care about it. You can always get back to the documentation. Of course, if you know how a model is working, it's a great idea. I advise you to do it. But for the moment, you wanna try, you wanna play with the different models and everything, but you don't care about how he's training. You just need to know how you can apply this, which is by calling the fit function on the training data. This is the idea. Okay, we have x, y, and you can do this again and again, yeah, to fit it and to get. Now you know how to train our model. Next step is to make some prediction, right? The prediction, you have two functions here. Either predict and predict proba. If we take the classifier that you have been trained here, as you can see, classifier.fit, we have already trained the model, and we wanna predict on the x-test, right? It's gonna give you some labels, 0, 1, 0, 1. We have seen this in the y. 0 means that the patient doesn't have heart disease. 1, it has. So it's giving you the labels directly when you use the predict function, right? But you can see that now that we have our predicted value, we can call it y-predict. In order to get a score, for example, the accuracy score, we're gonna compare it to the y-test, right? We have the test data. So we're gonna predict on the x-test, it's gonna give you y-predict, and this y-predict, you're gonna compare it to the y-test to see if our model is performing well on data it hasn't seen before, right? And it's gonna give you a score, accuracy, which is just the mean of if you have 10 samples, your model is predicting right 8 samples, it's gonna do the mean. So 8 divided by 10 is gonna give you accuracy of 80%. It's predicting with 80%. But scikit-learn proposes also another one, which is the accuracy score that you can use directly using y-test and the y-predict. So you don't need to do the NP mean between these two. Just call the accuracy score between y-test and the y-predict. And it's gonna give you the same score here, which is 80%. Let me just run this. Okay. But in reality, what's going on behind this? The predict proba function gonna give you the answer. How our model was able to predict 0 or 1 is just probability. The idea behind this, what's going on, is doing this, doing the classifier prediction probability. Let's try to predict the 5 samples from test set. If we take the probability prediction, you're gonna see that it's giving us 0.89 and 0.11 for the first one. What does it mean? It means that it's probability for the first label, which is the 0, the class 0, and the probability for the second class, which is the class 1. So this is how we were able to get these labels. We see that the probability to get the class 1 is very high. This is why he predicted 0. For the second sample, you can see that 0.51 for the class 1. This is why he gives you the second label 1. Why we are choosing 0.5 as threshold? I mean, it's better than guessing. Guessing is 0.5. If it's at least better than guessing, we attribute this to the class. This is the idea. Why he's using 0.5 to class, to do the class here, to predict. So again, if you take only one sample here, if you can see, this is for the 5 samples. This is how he was able to get the 0, 1, 1, 0, 1 by doing these probabilities and saying that, okay, for the sample 1, here, 0.89 is very high than 0.5. This is why I'm attributing this prediction, 0. And this is going to give you the same thing here. As you can see, if we take x-test only the first sample. Again, why we use 0.5 is because it's better than guessing. This is the idea. And now we know how to do it. So again, we have our prediction. And it's going to be the same thing for the regression, right? Now we were working with classification problem. We were using an accuracy score. But for the regression, it's the same thing. You're going to have your y predict, if it's a random forest regressor model, for example, here. And you're going to use a metric which is mean absolute error to measure the performance of our model, if you are working with the regression, for example. OK, now let's move to the next step, which is the evaluating the model. OK, so the idea here, we're going to have a score function and this cross-validation function that you're going to see. This is very important, what we're going to say for the cross-validation. We're going to start with the score function. If you take the same model, the random forest classifier, the heart disease, same. When we're going to do this, train our model and directly using classifier.score on the test, what he's doing by default is using the accuracy score as parameter. This is the metric that the model is using for the classification problem by default, the accuracy score. Right? So here, this was for the classification. For the regression problems, the one by default that you're going to use here in the metric score is the R2 score. Again, if you want to learn anything about these metrics, you can go to the documentation, of course. But by default, you're going to use the metric R2 score. What you need to know for the moment, the best possible value is 1. This is what you are looking for. Now, I've been talking about the score method by default. OK. But now we're going to see the cross-validation score, which is very important. Why? For the moment, if we train our model, we know how to do it. We do the scoring on the test set. It's going to give you 85% accuracy, right? It's going to give you 1 score. But what we are looking for in order to make a model very robust and performing very well, to get really how our model is performing on the data, we need to use the cross-validation. Why? If we took this cross-validation and we give us the x and the y, it's going to give us 5 score. OK, why? What's going on? The idea is this. What we are doing from the beginning is taking our data, 80% for the training, and 20 for the split, right? And then we're going to get a score. But do we really get a score that really said how our model is performing on our data? Not really. Imagine you split your data randomly and you get only easy samples. You're training your model only on easy samples, and you're going to perform very well. You're going to be happy. But this is not the case. Your model is not performing maybe very well on the data. Why? Because you get only easy samples. This is why cross-validation is very important. What he's going to do, you're going to each time divide your samples here, 100 for example, into 5 folds. And you're going to change the test. You see? You're going to start with this one and train on this. Train on this and test on this. Train on this. Yeah, this is what I was trying to say. That not train on, your model is not trained on all the data when you are splitting only one time. And avoid getting lucky score on single split, which doesn't represent how our model is performing really. So always work with the cross-validation score. So for that, it's going to give you 5 score. Why 5? It's chosen by default. Again, you can change it as much as you want. But by default, we are dividing this into 5 folds. Now, you can take the mean of this all, and you can compare it to the one single score. OK, we get an accuracy lower than the one in a single score, which is okay. We don't care about the result here because it doesn't represent our model, how it's performing on the whole data. This is the real score that represents our model, how it's performing on the whole data that we have. So we always prefer the close validation score instead of this one. Okay? Now, we know how to use the cross-validation score, but again, the cross-validation score has a parameter called scoring here. By default, it's using the accuracy. But again, you can change it, and these are the different metrics that you can choose. You have accuracy, you have the area under the curve, which we're gonna see, the ROC function, confusion matrix, and classification report. This is different metrics for the classification models. Let's see an example. Here by default, again, it's gonna give you the accuracy. We have seen this. Let's move to the area under the curve. The area under the curve is gonna use these parameters: true positive, false positive, true negative, and false positive. It's gonna be based on this in order to create the area under the curve. Let's see an example directly. It's gonna be easy. We have a function that we can call, which is the ROC curve, that you can use already, provided by scikit-learn. And then you're gonna have a function to plot this. You can use it, I already did it. And it's gonna give you this graph. What you see here in blue is the guessing. And this is how your model how is performing. And this score, it's called area under the curve. It's calculating this area. And we have already a function to do that for us, which is great. We just give him the whitest and the white probability, that's the prediction. And it's gonna give you the score, which is 0.9 here. What you need to know is the perfect score is 1, and it looks like this. If you give our ROC curve whitest and whitest to compare, it's gonna give you something like this. This is why it's equal to 1. So this is another metric that you can use, right? You can use accuracy and the area under the curve score. Okay, great. Let's see another one. Confusion matrix. Confusion matrix is going to be the same. It's going to use what we have already seen, the true positive, true negative, and it's going to create you. We have already a function for it, confusion matrix also. It's going to give you this matrix. Let's make it better looking. Again, it's going to give you this. The predicted labels, 0, 1, and the actual labels. And you can see that he got true positive 24, right? And 28, right, for the class 1. And he got wrong 5. Its actual label is 0. He's predicted 1. And here the actual label is 1. And he's predicted 0. So for the whole samples, he's making 9 wrong in the prediction. This is good to use also to give you an overview and idea how your model is performing, right? And it's more visual also. You can see it here. You have some function like this one. To give you the number of true prediction and where he's missing or getting the prediction wrong. But again, accuracy, area under the curve, confusion matrix, they are good. But the most important one is the classification report. Why? Because it's going to give you the whole thing in one time. It's going to give you the accuracy, the F1 score, the precision, and the recall. Why is it important? Why the recall and precision is very important? Think of it like this. Imagine, let's say, you're going to have 10,000 people, and one of them has disease. And you are asked to build a model to predict this, right? You're going to do it. You build your model, and you get an accuracy of 99.99% accurate. you're gonna say it's amazing. I did perfect model, right? It's the perfect. No one gonna beat me. But until you realize that all what you are doing is predicting that no one has a disease, right? In other words, the 10,000 prediction are false, which is very, very bad. Like you are doing. This is why precision and recall is very important. Why? Because imagine you create this scenario, 10,000 0, and one disease equal to one, only one case. And then the disease prediction, he predicts only zeros, right? And we build our classification report on this. You're gonna see that the accuracy is amazing, 99%. For the class one, for the class 0, right? 99%, amazing. F1 score, same thing. But when you're gonna look to the precision and recall of the class 1, it's very, very bad. It's 0, which is, this is why I'm telling you, always use classification reports. It's very important because it's gonna give you overview and a good idea about the different parameters, how it's and model is performing, right? So again, use always classification reports. It's gonna give you precision and recall, and here you can get a better idea. Now, regression has also some metrics, which is R2 score, mean absolute error, and the mean squared error. Same thing. If you take the house in the data frame, you're gonna have the R2 score that you can use by default here. And yeah, here I'm giving you another example how it's working. If you take the y-test and the y-test mean, it's gonna give you 0. This is how R2 score is working. It can be calculated, yeah. The model which only predicts the mean, it's gonna give you a 0 score. This is the idea of the R2 score. Mean absolute error, same thing. I think I'm not gonna run it because it's gonna take some time, or it's, let's try. Okay, it's okay. So again, scikit-learn proposed this, the mean absolute error, and you can use it between y-test and the y-predict. You can use some visualization like this in order to get an idea about how your model is performing between the true value, actual value, and the prediction. And finally, the mean squared error, same thing, between y-test and y-predict. So these are the different parameters. Now you remember the cross-validation score function. It has, as I said, scoring parameters there. If you remember, I told you by default, it's using the accuracy. But now that we know that we can try and use other metrics, the idea gonna be to use this cross-validation here and change these parameters, the scoring one, into the function from accuracy to precision to recall to F1, you see? And now it's gonna give you better results, very robust results, because it's gonna do the cross-validation. It's gonna split the data into 5 folds and do the prediction and give you a score that you want, the precision, accuracy, recall, F1, and do the mean. And it's gonna give you a better view of your model, how it's performing, right? This is the idea. Try always to work with the cross-validation and choose the metric that you wanna see. But again, try always to use them all in order to get a better view of how your model is performing, not only the accuracy. Same thing goes for the regression. You're gonna have the R2 score, the mean absolute error, and the mean squared error. I'm not gonna run them because it's gonna take a lot of time to do it, because it's gonna split the data into 5 and do this. But you get the idea, right? Now, using different evaluation metrics, so using scikit-learn. Scikit-learn, I'm giving you all the option here. Scikit-learn proposes also this, and you can use them using this function, accuracy score, precision score, recall, and F1 score. And this is gonna give you already this. And for the regression, same thing. Scikit-learn proposed this. All right, now you know how to do it with scikit-learn and different functions. Next step is how you're gonna improve. Now we train it, we made some prediction, let's make it even better. How we can improve our model now? By doing some hyperparameter tuning. For that, let's see an example. I'm going to use always the classifier random forest. If you remember, each model has hyperparameters that you can tune and play with it. If you take a look to our parameters of random forest, we do classifier.get parameters. You have this. This is the parameters that you can play with it in order to get a better model, right? But again here, if you see, we're gonna try to select some of them and play with them. Maybe the max depth, the mean simple split, the n estimator, and see how our model is gonna be performing, right? For this, you're gonna have 3 methods. First one, by doing it by hand, which is a bad thing. Don't do it. I'm just showing you. Like, you are the one who's gonna change the model parameter and test. Don't do it. It's just an example. Then we're gonna see randomly using random search CD. And finally, exhaustively with grid search CD. What I mean here, let's see an example. If we take these parameters, you remember the train validation test split? We haven't done this before, right? We're just working with training and test. This is just purpose of just show you some examples. But in reality, you should always work with this. This is how you should work. Training, validation to do the tuning, and finally the test, right? Let's do it. We have our parameters. We're gonna select this one that you're gonna try to adjust. Define some evaluation metrics that you're gonna use later. And this is the idea. All right, let's see here. We're gonna create our train split, which is 70% of our data, right? A validation split, which is gonna be 15%. And then we're gonna create X train, Y train, X validation, Y validation, and then X test and Y test. But you can see that it doesn't look very good, right? You are doing it by hand and you are splitting by yourself. It's not good. It's not the right way of doing it, right? And again, the best thing that you can do, if you remember, is the cross-validation, right? I told you, don't split only one and get lucky with the good results. Always work with the cross-validation. This is the right way of doing it. You have your data. You're gonna split it into training and test. Let's take 80% for training and 20 for test, right? Okay, we move test, we forget it. You're gonna take your training data and do cross-validation on it. And now you can tune on the cross-validation, right? You can split it in different split, like 5 here, as you see. You're gonna test it on this and train on the green. Then you're gonna test it on fold 2 and train on the fold 1, fold 3, 4, 5. You're gonna do the cross-validation on the training here. And finally, when you get really good model, you're gonna test it in the test data, right? This is the right way of doing it. How we can do this? All right, let's see. Again, we're gonna take our X and Y. You remember? You know how to do it. We're gonna split our data into X train, X test, Y test. Here we're gonna take for the test size 15%, right? Okay, now that we have our X train and Y train, we can apply, remember, the cross-validation score on it. And it's gonna give you the right scores. This is how you should do it, always, right? You take the cross-validation and you apply it into X train and Y train, and it's gonna give you the score mean which is going to represent how our model is performing in real, the whole data, which is the training in our case, because I told you, test, we forget it. We don't wanna touch it. And it's gonna give you some metrics. Here, the mean cross-validation score is 0.82, which means this is how our model is performing on our training data. And then you can apply this to get the prediction by using this classifier on X test, and it's gonna give you the right accuracy or the scores, how our model is performing on test data, which is in this case, 78% on the test data. All right, now we have a methodology. The idea, let's try to improve this 78% accuracy. How I can do it? We can tune this. Again, first option that I said is by hand. For that, let's take our model, remember, the random forest, and let's change this n estimator to 50. I told you, we can do it by hand, so I'm choosing 50 estimator. Let's see how we're gonna perform. Okay, we get a better score, 80%. We were able to improve it, right? But we did it by hand, which doesn't make sense, right? It's just to show you. The right way of doing it, of course, is using randomized search CV. Let's see an example. I want our model to test it for these different parameters. I choose the n estimator, max depth, max features, mean, and mean sample. And I give him some numbers that I want him to test on it. And I'm creating dictionary, right? Now I have a dictionary with all the parameters that I want our model to test. But again, if you look at this, if you do the calculation, you can see that we have 5 here, multiplied by 4, multiplied by 2, by 3, by 3. So we have 360 models to test, right? It's a lot. Random search CV, what he is proposing is that you're gonna choose a number of models that you wanna test. Maybe you wanna test only 30 models or 20 models. And he's gonna choose randomly between this dictionary, randomly parameters that he's gonna choose. You're gonna choose these parameters randomly, and you're gonna create these 20 models that you're gonna try to test on it, right? So for that, let's see an example. We have our dictionary. You're gonna do exactly the same thing. You have your classifier, which is a random forest classifier here, and you're gonna use the function called randomized search CV. You give him the classifier, so the model. You give him the dictionary, so the parameters that you wanna test on. And iter is the number of the models that you want to try. In our case, I told him to try only 20 models, right? But what is good on using randomized search CV, it already has the CV function, which is the cross-validation. So it's doing it for it's amazing. It's doing it for us. We don't need to do the cross-validation thing. It's already there. So for each model, the 21, you're gonna do the 5 cross-validation. So it's gonna give us 5-fold for each 20 candidates, which makes 100 fits. So you're gonna test for us 100 models, because for each model, you're gonna do the cross-validation, which means 5 folds, right? And you're gonna give us a score. I'm not gonna run this, it's gonna take a while. So you can see the result here is going through the different parameters, but this time randomly. Gonna choose for us 20 models with the dictionary that you have given us, and you're gonna test on it. And you're gonna give us the best parameter and the best model, which is amazing. So you're gonna test for us, and you're gonna give us the best model. And you can see that you are able to get 82% this time. So we were able to improve our model just by using randomized search CV, right? Okay, now imagine You wanna go through the whole thing. You don't care about the random thing. You wanna go through different parameters. So the 360 models. You're gonna use grid search CV. If you have enough resources, you can do it. So you can go create your grid, which is the dictionary again. It's the same one here. We have 360 models. I reduce it a little bit just to get 72 models that I can run. And I'm gonna use the grid search CV this time, not randomized search CV. So I'm gonna test on 72 candidates, 72 models for 5 folds, because we are doing cross-validation. It's gonna give us 360 fits, which means 360 model. You're gonna try 360 models. And it's gonna give us a result. Let's see how it's performing. Okay, it's gonna give us the best parameters and the best model. And this time it gives us 80%. Okay, why? Because again, I'm the one who chose the parameters that I need to change, the dictionary. But you should remember something. In general, the default parameters that the model is using are very good. They're doing it in a way that you get a good score, right? So you can always play within it, change some parameters that you are sure that it's gonna perform, give you a better model, get back to the documentation to choose the parameters. It's always good. This is how you can do it. But in general, keep it in mind that the model default parameters are very good. This is the idea. But you can always play within it. And it's gonna give you something like this. A baseline, we have seen that it was performing 70%, which is not good. And we were able to get classifier using random search CV in green, which performed the best. Okay, this is how you can improve and tune your model. This is the kind of stuff that you can do. Now you can go a little bit further by choosing and working on some advanced model like the XGBoost. Okay, if we train our model into XGBoost, it's not randomized. It's not random forest. It's another very robust model. It's called XGBoost. You have also CutBoost. And if we do this and train it, do exactly the same thing, I get already 0.86. Amazing. So we were at 82 and we moved to 86, which is amazing. Now again, I know how to choose these parameters. This is why I get these scores. I already did the grid search CV and all this thing to get the best parameters. This is why I'm getting this. How you can get this kind of models? Same thing. We're gonna take our model, do the cross-validation, which is gonna represent, again, here it's representing only one split, which is not good again. This is why we get a very good high score. The idea is to always use the cross-validation, right? Here it's gonna give you the right scores using the cross-validation. It's 0.82. How you can improve it? Same thing. You're gonna create a grid, classify a dictionary using these parameters, train it using grid search CV or randomized search CV, and now it's gonna give you here, for example, 540 fits. It's a lot. It's gonna do the fit for us this time using XGBoost, which is more advanced model, not random first. And at the end, we're gonna be having these results. It's gonna give us the XGBoost best parameters and the best model, and we get this, 84%. So we were able to improve it from 82 to 84%. And this is the kind of graphs that you're gonna have at the end. The XGBoost is in the purple, is the best one. Just to give you an idea, this is how you can take it a step further, right? Just by doing and improving and tuning your models. All right, now we have seen how we can move from the beginning into tuning the model. Last part is how you can save it. Again, here's some function that you can use. It's called the pickle one. So you can save it using the pickle. I'm giving you all this. Again, you can go back to this and read the commentary. I made a lot of comments here, so you can do it by yourself again. But this is, I'm showing you the overview, so you can save it using pickle and load it again, right? Pickle.load, and you can have your XGBoost saved. If I do this, it should be loading the model, and I'm getting the same results, right? You see? I already trained this model, and I'm getting the same results without training it, because I save it. This is very good when you are working on something very huge, and you don't have the resources, don't have the time. You train it, you save it, then you call it again, train it again, save it. You see, this is how you can do it. This is very important. You can do it also with JobLeap. I'm giving you other functions how you can save your models, either with Pickle or JobLeap. Same thing. You can load it and apply, and you're gonna get the same results. Now we finish everything. We go from 0 to the end. Let's make the last step, which is the pipeline, the framework. We know how to do all this. We have our data, missing thing, dealing with the missing thing, categorical thing, all this. But at the end, you can create something like this, which is a pipeline using the function pipeline. I'm not going to enter into the details, but just know that now that we know all these steps, you can create something like this one. We're going to do the whole thing that we have seen, dealing with the missing value, converting, doing the cross-validation, creating a lot of all the steps that you have seen using the pipeline function here. You create something called preprocessor. You can go to the details if you want, but the idea is that you're going to create the categorical features, the numerical features, give them what you want, the strategy. Is it a constant, a mean, and then apply to the features that you want to use here, and you create a pipeline going from preprocessor, and then choose a model, and just apply this, and this is going to do this for us. The preprocessing and the modeling part, both in one cell, in one pipeline here, like this one. And when you're gonna get something working with this pipeline, the idea, it's simple now. You have a pipeline, you just change a model, and you train and test different models. So you have the pipeline that works great. We know how to deal with everything. You create a regression models here, a dictionary, with different models that you want to test. For example, ridge, Bayesian, linear, lasso, XGBoost, random forest. And you apply, this time this pipeline, you're going to do a loop that's going to go through this pipeline and changing the model from this dictionary. So you can see that easy. Just by having this pipeline, this kind of stuff, you can create the different model that you want to test, and you can go through it using just loop. And it's going to do this fitting for the different models. And it's going to give you some results here. So we have these results, okay, right? For the different models, just in few steps, which is amazing. Again, you need the resources, but it's amazing. You have the pipeline, do Booker 4, just a loop, and you're gonna get the best different scores for different models. And you can take it a step further by, now that you have the different models, okay, you can see that, okay, the ridge, I like it. The XGBoost, I like the results. You take it a step further and do some grid search CV using the pipeline to take it even a step further. So it's gonna have something like this, a very complicated thing, but it's gonna you're gonna choose the parameter that you wanna change in the model. So this is good to start choosing different models, get an idea about the model that performs very well. And then the next step is taking this model a step further by doing some hyperparameter tuning, as we already see, using the grid search CV. And this is going to give you a good score. And you're going to choose, imagine there are two models that performing very well. So you have two models that you like. The last step, and I will finish within it, is to combine this. You can do it using these two kind of stuff, either stacking or voting model. And you can combine the two that you like the most. Try always to choose the one that are different architecture. That way, you can combine them using a stacking or voting method. It's already in scikit-learn. Just put the model 1 and model 2 that you like the most, and let him do the trick here and get you the best model that you can have by combining the two best models here. And at the end, you can create something like this, a pipeline that do everything for you using the stacking and the voting. And here you get the best final score, right? So this is it for today. I hope you enjoy it. I know it's a lot to digest. Again, you need to practice by yourself. This is machine learning. You need to practice. I put you here some Jupyter Notebook exercise that you can exercise by yourself. Try to go through this alone by yourself. Read the commentary. I put a lot of comments. You can do it by yourself, and I hope you enjoy it. Thank you again. Thanks. Thank you. It's